Hai, Assalamualaikum and selamat tengah hari. Okay, so we will continue the lecture about the sun. Okay, so we continue with this slide. Okay, slide 40. It's about the solar cycle in a solar magnetism. Okay, so we have learned about the phases which will be included in the solar cycle. We have solar minimum, solar maximum, and also we have in the phase of a solar minimum, we have another one we call as the mountain minimum here, as we can see from this figure. So this is due to the periodic reversing of the polarity of the sun's magnetic field, where the solar dynamo operates much faster and a much larger scale than planetary magnetic fields. So the 11-year periodicity of the solar sunspot cycle is actually far from the regular, so its period range from 7 to 15 years in the past. Okay, as we can see in this figure, so the variation of the estimation of this sunspot number here in the y-axis. Okay, so you have in the x-axis in terms of the year. Okay, 1600 to like 1700. We have the mountain minimum. That is very minimum value of sunspot number, so we call as the mountain minimum. And then go to the next one. So this mountain minimum is the sun was in a period of solar inactivity between 1645 to 1715 in history lah. So since that, it's called the mountain minimum. And we have also the corona, okay, with less prominent during the total solar eclipse around the mountain minimum, okay, around that time. And the Earth's aurora will sparse throughout the late of 16. So this inactivity of the sun is not well understood, okay, and true it is suspected to be caused by the changes in the sun's convection zone or the rotation pattern. So this is the two issue that is important in the sun aspect when we are talking about the changes happen on the surface of the sun, the phenomena which happen on the sun's surface. So it's very important to relate these two aspects here. And has the recent sunspot minimum in 2008 has resulted in the least active sun in almost a century. Okay, with that, there's no sunspot were seen on 80% of the days. Okay, so and the solar wind was anomalously weak. Okay, because there's no observation on the sunspot. Almost 80%, they can't observe any of the sunspot at that time. So it's called the sunspot minimum. So the current sunspot cycle, we have 2019 to 2030. Okay, it's named the solar cycle 25. So now we are in the solar cycle 25 and numbered by the Rudolf Wolf. Okay, is an astronomer who recollected the sunspot observation data way back to Galileo's time in the 16th. Okay, so for the cycle 1, okay, it's started between this range of time, okay, as it when the first extensive recording of solar sunspot activity existed. So since that, there is reported the very first solar cycle. So we go to the next one about the active sun. We have the active regions on the sun's surface. Okay, we have these energetic events. The eruption happen, okay, on the sun. They are mostly associated with the sunspot, okay, and frequent and violent around the solar maximum. So if we're talking about the solar maximum, okay, so we can assume that the sun is very active itself on the surface. So we can observe many events that might occur at that time for solar maximum. Okay, so as an example, we have this prominence. Okay, it's one of the space weather. Okay, the loops or sheets of glowing gas eject from the active region here. Okay, on the solar surface and caused by the magnetic instability in the strong field in or near the sunspot group. So we can assume that these two pole that connect these 2 points here, okay, is from the sunspot itself. So maybe have some magnetic instability happen in this side and cause them to be combined together like this, okay, and have a ring, okay, the link for the two area sunspot group. And as a theoretical, it's a very hard to study since the structure change too rapidly. Okay, and we have also the quiescent prominence persists for days or weeks, while the active prominence come and go erratically in hours. So many changes happen in a very short time. Okay, so a typical solar prominence measures about 100,000 kilometer in extent and release up to 10 power of 25 joule of energy, so very high energy. And then next one we have solar flares, okay, very famous space weather called solar flares. So it's observed low in the sun atmosphere also due to the magnetic instability, and more violent but less well understood than prominence. And it features like a flash across a region in minutes, but release as energy as prominence. Okay, it does for weeks. The temperature reach 100 million Kelvin, and it's responsible for internal pressure wave that create the solar surface oscillation. Okay, the explanation behind this to happen. Okay, so next one we have CME, okay, the coronal mass ejection. It's a giant magnetic bubble of ionized gas that separates from the rest of the solar atmosphere and escapes into the interplanetary space. Okay, so this is the CME. You can see this figure. Okay, so it occurs once a week during the sunspot minimum also, but 2-3 times a day of solar maximum. So we can see the different any of this space weather happen when the event occur at solar minimum or solar maximum. So if solar minimum, this happen reported about once a week, but if it is in solar maximum, it can happen 2 to 3 times a week. Okay, so that's when the sun is very active during the solar maximum. So if the magnetic field is oriented in the opposite direction of the Earth, so it could merge with Earth's field via reconnection and potentially causing widespread communication and power disruptions to happen. Okay, we can see also in this illustration, okay, we have this the Earth for B here. Okay, when the CME happen, okay, the magnetic field on the CME area, so it will pull into the from the to the Earth, okay, from the sun lah, this EMP from the sun, okay, it might go to the area near to the area of the Earth, and also magnetic field on our Earth, okay, might be disrupt, okay, the signal or communication. And okay, now we have these red regions depict the high energy charged particle, okay, here, and the charged particle will enter our Earth's magnetosphere. So it will become like this. So it's distort lah. There's somehow they disturb our magnetic field line. So it's very dangerous thing. Okay, so the changing solar corona. Okay, we have the hot coronal gas. Okay, radiates primarily in the X-ray range. Okay, using the X-ray telescope. Okay, so we can see the hot coronal gas, how it radiates in X-ray range. And also was found the solar wind escape mostly through the solar windows, okay, called the coronal holes. So these coronal holes are the vast regions of the sun's atmosphere where the density is about 10 times lower than the already tenuous corona. Okay, we can see the field lines. Okay, when the particles are trapped here, okay, and field lines extend into interface space. Okay, the rest yang not trapped in this area, then the particles will escape to the space. Okay. So normally, if any disturbance happen, prominent solar flare and so on, they will trap the particles here. Okay, so it not lost into the space. So that is the issue, or we have to take a look about this one lah, yang why scientists want to discover or want to know more about this space where they can, how it can affect or give a bad impact to our Earth. So these coronal holes are lacking matter due to the magnetic disturbance. So this one is a magnetic disturbance happen in the sun's atmosphere and allowing gas to stream freely into space at high speed, up to 800 kilometers per second. So because of the open field structure in coronal holes, flares and other magnetic field magnetic activity tend to be suppressed there. Okay. So because of this open field structure in coronal holes, so will make magnetic activity will be suppressed. Okay, so the largest coronal holes about can be 100,000 kilometer, okay, and maybe survive for many months, okay. And long-lived coronal holes persist at the sun's polar regions over much of magnetic cycle. And the solar corona also varies with the sunspot cycle. So it is much more irregular in appearance and extends further during solar maximum. So for solar energy production, okay, we have this estimation on how efficiently the sun generates energy by dividing the solar luminosity by solar mass. So we have to divide these two parameters, and then you get the efficiency of the sun. So this means the average for 1 kg of solar material will yield about 0.0002 joule energy per second. Yeah, almost 2. Okay. Round off lah this one. would be 0.0002. And by multiplying this rate with the sun's expected lifespan, we get this, okay, for the total energy of the sun that will generate through its entire lifetime. Okay, this is a solar energy production, and then we have this the nuclear fusion. Okay, so how this nuclear fusion reaction happen? So it's symbolized presented as a nucleus 1, nucleus 2, and produce the nucleus 3 plus the energy. So part of the mass from nucleus 1 and 2 is converted into energy here through mass energy equivalence. Okay, I know you have memory of this expression E equals to mc squared, which in turn is an example of the law of conservation of mass and the energy. So the fusion reaction in the solar core causes the energy to be produced in the form of electromagnetic radiation. Okay, while the mass will slowly decrease with time. Okay, so the fundamental forces, okay, the behavior of these four fundamental forces. Okay, first one is gravitational force, about gravity. Okay, the attractive force that binds galaxies, stars, and planets together. And magnitude decrease with distance and increase with mass. And the weakest of the force of nature, but its effect is greatest at large scale, and nothing can cancel its attractive. For electromagnetic force, okay, we have this electric charge, electron, proton, and magnitude decrease with distance, usually unimportant on microscopic scale, and can repel as well as attract like charge and the opposite charge. We have the weak nuclear force, okay, that governs the emission of radiation from some radioactive atom, does not obey the inverse Pareto law, and only effective within the size of atomic nucleus. Okay, and we have the electromagnetism. Okay, it's a electroweak. Okay, they have distinct properties at low temperatures, but indistinguishable at very high temperature. Okay, and then we have this strong nuclear force. Okay, that binds atomic nuclei and subnuclear particles together, governs the generation of energy in stars, operates only at very close range, which define the size of atomic nuclei, and also attraction turns into repulsion. Okay, so very loosely speaking, the strong force is, okay, you can read this 3 points here for electromagnetism, weak force, and the time. Okay, for the charge particles interaction, okay, when two charged atomic nuclei collide at high speed, they get to a distance less than 10 power of -15, okay, from each other. So the attraction, the strong force will overwhelm the electromagnetic repulsion, and that is so called the nuclear fusion. Also defining the nuclear fusion in terms of charge particle interaction here. Okay, so you have this reaction. Okay, this reaction is quite important. Yeah, maybe I give you some clue for your final. Okay, so this is important. The diffusion reaction between the proton in the sun's core, and can be represented by the equation as follows. Okay. Okay. So about the deuteron, Okay, the nucleus of heavy hydrogen called the deuterium, it has extra neutron than ordinary hydrogen. Okay, how about positron? We have E plus positron, antiparticle of electron. It has a positive charge, and also the gamma ray photons. Okay, neutrino. Neutrino is VE. Okay, is a weak nuclear force. And isotopes also, I think almost all of you familiar with this term. Okay, so you have, for example, the ordinary hydrogen, deuterium, okay, normal helium, where the superscript is the nucleon number. Okay, so nucleon number is the number of proton plus the number of neutron. Okay, this one is important too for maybe for your final. Okay, the proton-proton chain. Okay, the basic set of nuclear reaction powering the sun is a sequence called the proton-proton chain, or the PPC. Okay, so maybe you have to memorize this, memorize or understand the expression or the reaction happen here. So the net effect is therefore, okay, for proton plus 2 electrons, so you get helium, okay, 2 VE and 1 gamma. So from this one, it's basically illustrate in term in the shape of figure. Okay, you got this. Okay, we try to understand from here from the expression or reaction like this to like this. Okay, so the sun's nuclear energy produced in the core started the form of gamma rays. Okay? However, it passes through the cooler interior. Photons are observed and re-emit, causing the radiation of black body spectrum to shift toward the lower temperature and longer wavelength. So it's Wien's law. Okay. So eventually leave the photosphere, mainly in the form of visible and infrared radiation. So a comparable amount of energy is carried off by the neutrinos, which escape the unhindered into the space. Okay, so the proton-proton chain is a comparably simple reaction and produce almost 90% of the sun's luminosity. Okay, so this will call back for the energy generation for the PP chain. Okay, so the total amount of energy released, okay, can be found using this EMC squared. Okay, the calculation. And therefore, the difference in mass here and the energy release. Okay, so this is the calculation for the energy. Okay, energy 4.28, so divided into 4 MP. Okay, the mass. Okay. Okay. So this process converts the 0.71% of original mass into the energy. And about 2% of this energy is carried away by the neutrinos, okay? And the rest appear as the gamma rays. Okay, is an example of solar luminosity. And mass consumption rate. Okay, I think this one you just maybe do some understanding about how to calculate the energy for mass. Okay, maybe not necessary to memorize. Okay, just have to understand, okay, for the calculation. But the most important thing, the PP chain, maybe you have to know how the reaction in the PP chain. Okay, so neutrinos, okay, neutrinos created in the PP chain are our best bet for learning about condition in the solar core. Okay, so some neutrino detectors use large quantities of chlorine or gallium to interact with the neutrinos, turning this nuclei into argon or germanium. Okay, this is the observation of solar neutrino. And the new nuclei are radioactive, and the detection of the radiation from their decay signal the neutrino capture. Okay, and we have this super camion candy looks for light produced when a high energy neutrino occasionally collides with electron, okay, in a water molecule. So this like example, you can see this figure. Okay, this one is a picture maybe from one of the laboratory about the solar neutrino experiment. Okay, as the high speed of electron move through the water, okay, it emits a faint electroviolet glow, which is detected by large photomultiplier tubes. Okay, so this is there is so many tubes here. Okay, from the tubes to the is basically going through from the high speed electron that moving through the water. Okay, so it's detected by these large photomultiplier tubes. Okay, so the probability of a given neutrino interacting with matter in the detector is only 1 in 10 power of 15. So therefore, large amount of water and long duration experiment are needed. So it's very difficult experimental. Okay, we can say because of the ratio is very small ratio to be detected. Okay, so that's why there's so many tubes prepared here. Okay, to be ready to maybe observe 1 from 1,000 billion amount of the probability of neutrino that can be observed, that can be absorbed from these multiplier tubes. Okay, that is just a ratio from the experiment. The biggest laboratory for neutrino observation. Okay, so although the solar neutrino have been observed, the number of solar neutrino reaching the Earth is about 50 to 70%, okay, less than the prediction, okay, of the standard solar model. So this means that either solar neutrino are not produced as frequently as we think, or not all solar neutrino will make it to the Earth. Okay, the discrepancy is known as the solar neutrino problem. Okay, and also have maybe proven in 2002 that the neutrino oscillation is the main source of the discrepancy of the problem, basically the solar neutrino problem. Okay, so recap here, the neutrinos symbol, okay, VE, the electron with interaction dictates that the oscillate into one, okay, neutrinos during their 8-minute flight to the Earth. So actually it's the same, maybe the same particles of matter, but it's just a different observation, different location finding. So it's called a muon after 8 minutes that particles jump into the Earth. Okay, so this is one guy that conduct the observation for this neutrino also. Okay, you can read this. Okay, so this is the recap for this chapter. Okay, chapter of the sun. So you can read it. Okay, so I think that's all. Right. Okay, thank you, class.